Alright guys, so here is the class opener slash review that we're doing today, Friday. So the question is, are these three functions, are they growth or decay functions? And I throw a curveball at you at the end. If we look at this first one right here, by the way, if you're doing this at home, please pause it, take the time to think about it and answer it, and then play so you can see the answer or hear the answer. So in this one, is it a growth or a decay function? It's definitely a growth function because the base is greater than 1. That's a growth function. Now you might be thinking, well, what about this negative sign right here? That negative sign is the a value. Okay, so the a value is -1. All that says is that it's going to get reflected on the x-axis. But the base is 2, which means it's a growth function. So this is a growth function growing in a negative direction. What does that look like? It looks like this. From left to right, it's going to grow, but in a negative direction. I'm not asking you to graph it. I'm just asking you to tell me if it's a growth or a decay function. How about this guy? Is that a growth or a decay? Well, that guy is definitely a decay function. Why is that? Because the base is less than 1. Okay? What does a decay function look like? Well, from left to right, it decays down to nothing. Of course, if it had a k value shift, then it would be approaching that asymptote, but right here there is no k value, so it's approaching 0. Oh yeah, but let's not forget about the negative sign, which is the a value of -1, which causes this graph up here to get reflected down here on the x-axis. Okay, so that's a decay function. That's what it looks like. Let's go for this one right here. This is a curveball trick question. Is this a growth or a decay? This is, a lot of us are thinking, even I thought this the first time, that it's a growth, but it's not a growth. It's a decay. What? Are you serious? Yeah, check this out. The base is 2. That is correct. But for the very first time, we have a negative x as an exponent. Now, what does a negative exponent do? It causes the inside value of the parenthesis to flip, to become the reciprocal. Let me just take you back to something really simple. Like if I had, what is 1/2 to the -3 power? This is back from Algebra 1 with the rules of exponents. Well, the negative that's up here is going to cause the inside value of the parenthesis to flip, to rewrite it as a reciprocal, 2/1, which is now to the +3 power because you already flipped it. And then after that you need to work on the exponent. So in this case it would just be 2 to the 3rd, which would be 8. Yeah, so that's, when you think of 1/2 to the -3 power, that's a fancy way of saying 8. Okay, so let's go back to this one up here. When we look at -2 to the -x power, that negative sign right there is going to cause this 2, which is really 2/1, to flip. So what you really have is y equals negative parenthesis 1/2 to the +x. So that definitely is a decay function. Okay, so this is a very interesting part right here, a very interesting truth, fact, that when your exponent is negative, you have to flip the base. Okay, so this guy right here is this one, same exact function. Okay, just rewritten. So taking a step back, comparing the second one and the third one, they're actually the same exact function. This guy right here is the same exact one as this guy right here. They just look different. And why do they look different? Because the exponent here is negative, the negative x is up here. And if you change it to positive, it'll actually become this same exact one right here. Okay? Let's move on. This next part of the class opener, we want to just describe in words how to find the inverse of a function. Okay, so how do we find the inverse of a function? Hit pause, write your answer, and then check your answer. To find the inverse of a function, switch x and y and then solve for y. It's that easy, right? So like if you had y equals 2x plus 4. You want to switch x and y, so you have an x here equals 2y plus 4, and then solve for y. Subtract 4, x minus 4 equals 2y. Now we still have the y not by itself, so we need to keep going here. Divide by 2, divide everything by 2, and you'll have y equals x minus 4 over 2, or another way of writing that, probably even a better way of writing that, would be y equals 1/2 x minus 2. Okay, that's probably the best way to write it. So here's the bottom line. This one up here is the inverse, or these two are inverses of each other. Okay, so what I would like to do right now is to compare an XY table, okay, of each. So let me do this red one right here. Let me plug in some inputs and outputs, some inputs and get out some outputs. Now because it's red, I'm gonna, or not because it's red, but because it has a fraction of 1/2 in front of my x, right? There's a fraction here of 1/2. If I plug in a 1, it's going to give me fractions. So let me plug in some even numbers so it'll be easy to do. So I want to plug in something like 2, and maybe I could also plug in 4, yeah? Or 0 is always easy to do. Let me do 0 also. So anyways, when I plug in 2, what do I get out? When I plug in 2 into here, it's going to be 2 times half, which is 1, and then 1 take away 2 is -1. Okay, now let's plug in a 4, right? Let's plug in a 4 into here. 4 times half is 2, and 2 take away 2 is 0. Okay, and now let's plug in 0. That's easy to do. 1/2 times 0 is 0, and 0 minus 2 is -2. So we have those 3 coordinates. Of course, there's an infinite amount of coordinates to that red function. But now let's go to the black function, y equals 2x plus 4, and let me make over here an xy table, and let me plug in some numbers. Let me start by plugging in 0. Okay, if I plug in 0, what will I get out? I will get out, think about that, plug in a 0 right here. 2 times 0 is 0, 0 plus 4 is 4. Now, I don't know if you noticed this, but this is something very interesting here. I plugged in a 4 and got out a 0. Over here, I plugged in a 0 and got out a 4. So what do you think is going to happen if I plug in, let's say, a -1? If I plug in a -1, check it out. 2 times -1 is -2, and -2 plus 4 is +2. And if you look over here, plugging in a +2, you got out a -1. Over here, plugging in a -1, I got out a +2. So what do you think will happen if I plug in a -2 into the input of this one? I'm going to get the output, which is the input of this one. Crazy, right? Let me just show you. Let me plug in a -2. And when I plug in a -2 right here, 2 times -2 is -4, and -4 plus 4 is 0. So what I want you guys to realize is that when you compare the actual coordinates of each of the inverse functions, what could you say about those actual x and y values? You could say that they have the same exact x and y values, but they're just switched, right? I mean, look at this. These x values right here are the y values over here. Look at these y values right here. They're the x values over here. Now, why is that? It all goes back to the way that you find inverse functions. How do you find inverse functions? You switch x and y. So the reason why I'm doing this is so you guys could understand that even if you didn't have an equation like this, like y equals 2x plus 4, right here you found the inverse by switching x and y and solving for y. But even if you didn't have an algebraic equation, even if you didn't have a function, even if you just had coordinates, and I asked you to find the inverse of those coordinates, all you have to do is switch the x and y values and you have your inverse coordinates right there, right? So let's say I gave you those three coordinates right there, negative 2, 0, 0, 1, and 2, 2. And let's say that was a line or whatever function, right? But let's say I told you to find the inverse of those coordinates. Well, it'd be simple. The inverse of these coordinates right here, it'd simply be 0, negative 2, 1, 0, and 2, 2. Because if you switch 2, 2, it's still going to be 2, 2. So let's just plot those. 0, negative 2 is right here. 1, 0 is right there. And 2, 2 is still right there. Okay. So your original line was something like this, and your new line is something like this. Okay. Now, these are inverse graphs of each other. Okay. What does that mean, they're inverse graphs of each other? Well, the inverse graph actually is a reflection on the line y equals x. This line y equals x, which makes total sense, because if you're able to switch the x and the y to get your inverse, that's only because y equals x. I know that's might be a little too confusing, but I just wanted to give you a little taste of what inverse functions look like when you graph them. They really are a reflection on the y equals x line. And the y equals x line is this yellow one, which now I'm doing, well, I shouldn't go red. Yeah, it's that yellow one right here. It's the diagonal that, well, that's disgusting. Okay, I'm sorry. But yeah, y equals x line is that diagonal that crosses right through the origin. Okay, and the inverse functions become reflections over that y equals x line.